Imagine for a moment what humanity could become. Engineers of some distant century, standing on the surface of a planet that is not this one, looking up at a sky containing stars we have never named. Dyson spheres wrapped around alien suns, harvesting the output of entire stellar systems. Civilizations spread across dozens of solar systems, hundreds, thousands. A galactic federation of human worlds stretching from the core of the Milky Way to its outermost arms. Going further, looking up from the surface of our home galaxy and wondering what lies beyond it. Sending ships to Andromeda, to the Triangulum, to galaxies so distant their light left when the first life on Earth was still single-celled. Humanity as a truly cosmic species, not bound to a single star or a single galaxy, but free to move between them as easily as we now move between continents. This is the dream that has animated science fiction for a century. It is the dream that inspired the space programs that built the rockets that put footprints on the moon. It is the dream behind every telescope pointed at the night sky, behind every speculation about what might be out there, behind every serious conversation about humanity's long-term future. Tonight, we are going to talk about why that dream is impossible. Not difficult, not far off, not waiting for some future breakthrough in physics that will finally crack the problem. Impossible, physically, mathematically, fundamentally impossible. The universe has built walls around us, and those walls are not engineering challenges. They are properties of space-time itself. There are 4 of these walls. Tonight, we are going to walk through each one of them slowly and patiently, examining how they were discovered, what they actually mean, and why no technology, no matter how advanced, can ever overcome them. The first wall is the speed of light, a limit so fundamental that it is built into the mathematics of causality itself. The second wall is the expansion of space, an invisible treadmill that is carrying the distant universe away from us faster than any ship could ever travel. The third wall is the cosmic event horizon, a boundary beyond which 94% of all galaxies that we can see tonight have already permanently gone. And the fourth wall is the heat death of the universe, the ultimate isolation of the Milky Way as every other galaxy we can see disappears into darkness, leaving future generations alone on a lone island in an empty sea. By the end of this video, you will understand with absolute clarity that humanity is trapped. Not temporarily, not until some future engineer solves it, but permanently, for the entire lifespan of our species, and any species that might follow us. Perhaps there is a strange comfort in knowing this. The rest of the universe is leaving us. For the rest of time, the Milky Way is all we will ever have, and perhaps in a very deep sense, all we will ever need to understand. The speed of light is 300,000 kilometers per second. In imperial units, that is about 186,000 miles per second. It is the fastest anything in the universe can travel. Not the fastest we know of, the fastest anything possibly can, because the mathematics of reality prevent anything from going faster. This is a number you have probably heard before. It is the kind of fact that gets mentioned in passing in science classes and on documentaries. The speed of light, 300,000 kilometers per second. A big number, an impressive number, but most people never sit with what that number actually means, why it exists, or why it is not just a limit, but the limit. Sit with it now. Light at 300,000 kilometers per second could travel from the Earth to the Moon in 1 1/3 seconds. It could travel from the Sun to the Earth in 8 minutes and 20 seconds. It could cross the orbit of Pluto, the farthest point in our solar system, in about 5.5 hours. These are impressive feats at the scale of a solar system. But the solar system is small. Light at the same 300,000 kilometers per second takes 4 years and 4 months to reach the nearest star beyond our own. That star is called Proxima Centauri. It is the closest stellar neighbor humanity has. And at the speed of light, it is over 4 years away. To put that in perspective, if you could invent today a spaceship that travels at exactly the speed of light, and you left Earth today at noon, you would not arrive at our nearest neighboring star system until after your 4th birthday since departure. And that is the closest star out of hundreds of billions of stars in the Milky Way alone. The Milky Way is about 100,000 light years across. That is the time it would take light to cross from one edge of our own galaxy to the other. 100,000 years at 300,000 kilometers per second. Andromeda, the galaxy nearest to our own, is 2.5 million light years away. Light leaving Andromeda tonight will not arrive at Earth until long after every human alive today is dead, and every human those humans know, and every human those humans will ever remember. The light we see from Andromeda tonight left that galaxy 2.5 million years ago, when our ancestors were still transitioning from Australopithecus to Homo. And Andromeda is close. It is the nearest major galaxy to our own. The universe contains hundreds of billions of other galaxies, some of them trillions of light years away. If humanity wants to become an intergalactic species, we have to deal with this number, 300,000 kilometers per second, the speed of light. The question is whether we can ever go faster. The answer is no. And the answer is not no with current technology. The answer is no as a fundamental property of the universe. Here is why, in 1905, Albert Einstein published a paper that changed how physics understood space, time, and motion. The paper was titled On the Electrodynamics of Moving Bodies. It was the paper that introduced what we now call special relativity. The central insight of special relativity is strange and counterintuitive. The speed of light is the same for every observer, regardless of how they are moving. If you are standing still and you measure the speed of a light beam, you get 300,000 kilometers per second. If you are moving toward the light beam at half the speed of light and you measure it, you still get 300,000 kilometers per second. If you are moving away from the light beam at half the speed of light and you measure it, you also still get 300,000 kilometers per second. This makes no intuitive sense. In every other case we know about, velocities add. If you throw a ball forward while running, the ball moves faster relative to the ground than it would if you threw it while standing still. Your speed adds to the ball's speed. If you shine a flashlight while running, you might expect the light to move faster than it would if you shone it while standing still, but it does not. The light moves at exactly the same speed measured by you in your moving frame and measured by an observer on the ground. This was confirmed experimentally before Einstein even wrote his paper. In an experiment conducted by Albert Michelson and Edward Morley in 1887, they were trying to measure the Earth's motion through what was then called the luminiferous ether by observing how the speed of light changed depending on the direction it was traveling relative to Earth's motion. They expected to find a variation in the speed of light depending on direction. They found no variation. The speed of light was the same in every direction, regardless of Earth's motion. Michelson's device, the interferometer he and Morley built in a basement at Case Western Reserve, was one of the most sensitive scientific instruments ever constructed at that time. It floated a solid stone slab on a pool of mercury, insulating it from vibration, while splitting a single beam of light into two perpendicular paths and recombining them to detect any difference in arrival time. If the ether existed, Earth's motion through it should have created an observable pattern shift as they rotated the apparatus. They found nothing, not a small effect, not a weak signal. Nothing for 18 years. Physicists tried to explain the null result with modifications to existing theory. None worked. The problem simply would not go away. Einstein took this seemingly impossible experimental result and asked, what would the universe have to be like for this to be true? What do space and time have to be like if the speed of light is genuinely the same for every observer regardless of their motion? His answer was special relativity. And the consequences of that answer were that space and time are not the absolute fixed backgrounds that Newton had assumed. They are flexible. They distort depending on how fast you are moving. Clocks tick slower when moving fast. Rulers shrink when moving fast. Simultaneity becomes relative, meaning two events that look simultaneous to one observer can look sequential to another. And most importantly, for our purposes tonight, one consequence of special relativity is that the speed of light becomes an absolute upper limit. Not a technological limit, not a limit waiting to be broken by some future invention, a fundamental limit built into the structure of space-time itself. The reason is energy. Special relativity tells us that as an object speeds up, its mass effectively increases. Not the amount of matter in it, but its resistance to further acceleration. The faster you go, the harder it becomes to go faster. At low speeds, this effect is negligible. At 10% of the speed of light, the effect starts to become noticeable. At 90% of the speed of light, the object's effective mass has roughly doubled. As you approach the speed of light, the effective mass approaches infinity, and infinite mass requires infinite energy to accelerate further. This is the core reason nothing with mass can ever reach the speed of light. To accelerate an object to the speed of light would require infinite energy, and infinite energy does not exist. The universe contains a finite amount of energy. No matter how you harness it, you cannot create infinity out of finite resources. Consider what this means in concrete numbers. If you accelerate a spaceship to 99% of the speed of light, the energy required is enormous but finite. If you accelerate it to 99.9% of the speed of light, the energy required is roughly 3 times as large. 99.99%, roughly 7 times as large. 99.999%, roughly 22 times as large. The energy requirement does not simply increase with speed. It shoots upward along a curve that approaches infinity as your speed approaches c. You can get arbitrarily close to the speed of light if you have enough energy, but you can never reach it because the energy required is infinite, and infinite does not exist. This is not a technological problem. This is a mathematical consequence of how space-time works. No future invention will change this. No theoretical breakthrough, no civilization, no matter how advanced, will ever build a ship that can travel at the speed of light, let alone faster than it. The speed of light is the universe's speed limit, and it is absolute. But here is where it gets strange. The speed of light is the maximum for anything traveling through space. Photons of light themselves, which have no mass, travel at exactly this speed. Massive objects cannot reach it. However, there is a quirk in how special relativity treats time for objects that are moving fast. This quirk is called time dilation, and it has interesting implications for interstellar travel. Time dilation says that the faster you move through space, the slower time passes for you relative to an observer at rest. This is not a psychological effect. It is not an illusion. Your clock literally ticks slower. Your atoms vibrate more slowly. Your cells age more slowly. Everything about your experience of time is stretched out when you move at high speeds. The effect is small at normal human speeds. A jet pilot flying at supersonic speeds for a few hours ages a few billionths of a second less than the people on the ground. The effect exists. It is measurable, but it is not significant for human experience. We know time dilation is real because we measure it daily. Every atomic clock aboard a GPS satellite runs about 38 microseconds faster per day than clocks on the ground because the satellites sit in weaker gravity and move slower than relativistic speeds. If engineers did not correct for this effect, GPS positions would drift by about 10 kilometers per day, rendering the system useless within hours. Muons created in the upper atmosphere by cosmic rays should decay long before reaching the ground, but they reach detectors at sea level in large numbers because their internal clocks run slower from our perspective. Particle accelerators routinely whip protons and electrons to speeds where time dilation factors into every calculation physicists perform. This is not speculative physics. It is engineering. At high fractions of the speed of light, the effect becomes enormous. At 10% of the speed of light, time passes about 0.5% slower for the traveler than for someone at rest, barely noticeable. At 50% of the speed of light, time passes about 15% slower. At 90%, about 57% slower. At 99% of the speed of light, time passes about 7 times slower for the traveler. A year of travel for the ship's crew would be 7 years on Earth. At 99.9% of the speed of light, time passes about 22 times slower. A year on the ship would be 22 years on Earth. At 99.99% of the speed of light, time passes about 71 times slower. A year on the ship would be 71 years on Earth. You can see the pattern. The closer you get to the speed of light, the more extreme the time dilation. In principle, a sufficiently fast ship could travel to Proxima Centauri, 4¼ light years away, in less than a single year of ship time, even though 4¼ years would pass on Earth. This creates an illusion that interstellar travel is possible. If time dilation is so extreme, then even though the speed of light limits us in terms of pure velocity, the subjective experience of the crew would be that the journey is short. A ship could cross the galaxy in a crew lifetime, even though 100,000 years would pass on Earth. This is the premise of a lot of science fiction. The relativistic starship, the crew that returns home to find everyone they knew long dead, but they themselves have aged only a few years. The promise of interstellar travel, if only we could reach relativistic speeds. Here is what it would actually take. To reach 99% of the speed of light, we would need to accelerate a ship to that velocity. Imagine the ship has a mass of about 100 metric tons, roughly the size of the International Space Station. To accelerate that ship to 99% of the speed of light would require approximately 6.3 times 10 to the power of 21 joules of kinetic energy. That number is so large it is difficult to comprehend. Here are some reference points. The total energy consumption of human civilization per year is about 6 times 10 to the power of 20 joules. To accelerate a 100-ton ship to 99% of the speed of light would require 10 times the annual energy consumption of the entire human race. And that is just for the acceleration. You would need another equivalent amount to decelerate at the other end. And this assumes perfect efficiency, which no energy conversion process in reality achieves. In practice, Because no reaction is perfectly efficient, you would need fuel. If you used chemical rockets, the fuel mass required would be astronomically larger than the ship itself. In fact, no chemical rocket can ever reach relativistic speeds because the fuel requirement grows exponentially with desired velocity. And at some point you cannot carry enough fuel because the fuel itself becomes so massive it requires more fuel to accelerate it. Nuclear fission rockets are better but still wholly inadequate for relativistic travel. Nuclear fusion rockets, which we cannot yet build but which are theoretically possible, could get closer but still cannot reach truly relativistic speeds. With any reasonable payload, the most efficient conceivable propulsion would be antimatter. Antimatter annihilates with normal matter to produce pure energy with perfect efficiency. An antimatter rocket could in principle reach very high fractions of the speed of light. The problem is producing antimatter. The most antimatter humanity has ever produced in a laboratory is a few hundred nanograms at a cost of billions of dollars per gram. A ship capable of reaching relativistic speeds using antimatter would require tons of antimatter. The total cost of that antimatter would exceed the total GDP of human civilization for thousands of years. And even if we could somehow produce it, we would have no way to store it. Antimatter annihilates on contact with regular matter. It would have to be contained in magnetic fields in perfect vacuum for years. Any failure of containment, even a microscopic one, would result in the annihilation of the fuel supply and the destruction of the ship. Even setting aside the cost and storage problems, there is a more fundamental issue. At relativistic speeds, every speck of interstellar dust becomes a missile. A grain of dust hitting a ship moving at 99% of the speed of light carries the energy of a nuclear weapon. The density of dust in interstellar space is very low, but not zero. Over the course of a multi-light-year journey, the ship would encounter enough particles that protecting against this bombardment becomes as challenging as propulsion itself. The fundamental problem here is captured in something called the Tsiolkovsky rocket equation, derived by Konstantin Tsiolkovsky in 1897. The equation relates the change in a rocket's velocity to the exhaust velocity of its propellant and the ratio of initial mass to final mass. Its practical consequence is that to increase a rocket's final velocity linearly, you need to increase its fuel mass exponentially. Doubling your desired speed does not double your fuel. It multiplies it by a factor that depends on how fast your exhaust leaves the rocket. But for any chemical rocket, the multiplier is enormous. This is why Saturn V, the most powerful rocket ever built, had to be 36 stories tall just to lift a small capsule to the moon. Almost all of that mass was fuel, and almost all of that fuel existed just to accelerate other fuel. For interstellar speeds, the exponential curve becomes impossible. Even with the best chemical propellants, the fuel required to reach just 1% of the speed of light exceeds the mass of the observable universe. For relativistic speeds, the curve goes to infinity much sooner, and then there is the cosmic microwave background itself. To a stationary observer, the microwave background is radiation at roughly 3 Kelvin, barely above absolute zero, completely harmless. To a ship moving at 99.99% of the speed of light, those same photons are blue-shifted into gamma rays arriving from the direction of travel. The ship is not flying through empty space. It is flying into a continuous wall of hard radiation that saturates the entire forward hemisphere. Any unshielded material at the front of the ship would be ionized. The crew would be cooked. There is no clear path from current technology to relativistic interstellar travel. The energy requirements are too high. The fuel problems are insurmountable. The engineering is beyond anything we can realistically build, and that is just for a single trip to the nearest star. But suppose, for the sake of argument, that all these problems are eventually solved. Imagine humanity develops some future propulsion system that can accelerate a ship to 99.999% of the speed of light with acceptable fuel requirements and adequate shielding. Every engineering problem solved. We still cannot leave the Milky Way because the speed of light is only the first wall. And before we move to the second, we need to understand why the first is so absolute. Why physicists are so confident that no loophole, no clever trick, no future discovery will ever open a door around it. The speed of light is not just a speed limit, it is the structural underpinning of causality itself. When Einstein formulated special relativity, one of the most unsettling consequences was what the theory did to simultaneity. In Newtonian physics, two events either happen at the same moment or they do not. Simultaneity is absolute. If two lightning bolts strike at the same time, according to an observer on the ground, they also strike at the same time according to a passenger on a train going past, even if the passenger sees them at slightly different moments due to the time it takes light to travel. Special relativity destroys this picture. According to Einstein, if two events are spatially separated, different observers moving at different velocities can disagree about whether those events are simultaneous. One observer can say event A happened before event B. Another observer moving at a different velocity can say event B happened before event A. A third observer moving at yet another velocity can say they happened at the same time. And none of these observers is wrong. All three descriptions are equally valid. This only works if there is a speed limit in the universe. If information could travel instantaneously or faster than light, this scheme falls apart. You could arrange situations where events could cause their own causes, creating logical paradoxes. The speed of light is the speed at which information propagates. It is the speed of causality itself. Any signal, any influence, any transfer of information from one point in space to another travels at most at the speed of light. If something could travel faster than light, causality would break. You could, in principle, send a signal to your past self. The mathematics of relativity is unforgiving about this. Faster than light travel is equivalent to time travel, and time travel creates paradoxes that the universe does not seem to allow. Here is the concrete scenario physicists often work through. Suppose two planets are a light year apart, and suppose you have a tachyonic radio that sends signals at 5 times the speed of light. You are on planet A and your colleague is on planet B, moving slowly relative to you. You send your colleague a message. From your frame, the signal arrives at planet B well before a light signal could have. Your colleague responds using her own tachyonic radio. On her moving reference frame, because of how simultaneity works between different reference frames, her reply arrives back at planet A before you sent the original message. You receive her reply to a message you have not yet sent. You now have a choice. Do you send the message you already received a reply to? If you do not, what exactly was your colleague replying to? The universe has no consistent answer. This is not a thought experiment dreamed up to make physics seem interesting. It is a logical consequence of the geometry of space-time combined with faster-than-light signaling. Physicists call it the tachyonic anti-telephone paradox, and it is why most of us believe faster-than-light communication cannot exist. So when we say the speed of light is the speed limit, we are not saying anything as mundane as our current technology cannot exceed this speed. We are saying that the universe itself is structured such that nothing can exceed this speed without also violating causality and creating logical contradictions. This is why it is so absolute. Not because we have not tried hard enough, because the alternative to this speed limit is a universe where effects can happen before their causes, where the laws of physics do not work the same way everywhere, and where causality, as we understand it, breaks down. Could there be some loophole, some way to travel faster than light without technically violating causality? Physicists have explored this. The most famous candidate is the Alcubierre drive, proposed in 1994 by physicist Miguel Alcubierre. Alcubierre was a young Mexican theoretical physicist who had grown up watching Star Trek, and he wondered whether warp drive could be formalized mathematically within the framework of general relativity. He sat down with Einstein's field equations and worked backwards. Instead of starting with a distribution of matter and asking what space-time it produces, he started with a desired space-time geometry and asked what matter distribution would produce it. The Alcubierre drive does not accelerate a ship to faster than the speed of light. Instead, it proposes to compress space in front of the ship and expand space behind it. The ship itself stays in a flat bubble of space, moving at normal speeds relative to its local environment. But the spatial compression ahead of it means that the ship can cross enormous distances in a short time, effectively traveling faster than light without any local object ever moving faster than light. This is clever. The mathematics of general relativity, as far as we can tell, do not forbid it. You can write down solutions to Einstein's field equations that describe exactly this kind of warp bubble. The problem is that to create such a bubble, you would need exotic matter with negative energy density. Negative energy density is something that does not exist in any form we have ever observed. Quantum field theory allows for very small amounts of negative energy in very specific circumstances, in what is called the Casimir effect between two closely spaced metal plates, but not the kind of bulk negative energy you would need to power a warp drive. The amount of negative energy required is also absurd. Alcubierre's original estimate required the mass energy equivalent of Jupiter to power a small warp bubble. Later refinements by Chris van den Broek and Harold White brought this down to something like the mass energy of a small asteroid, which is still far beyond anything humanity could produce. And even if you had the negative energy, there are other problems. A ship inside a warp bubble is essentially disconnected from the rest of the universe. Information cannot pass into or out of the bubble. The ship could not steer. It could not see where it was going. It could not stop the bubble once it started moving. Some analyses have shown that particles picked up by the bubble wall during transit would be released as a burst of high-energy radiation when the bubble dissipates, vaporizing any planet at the destination. A warp drive is not just impractical. If it could exist, arriving would be as destructive as a supernova. The Alcubierre drive is a beautiful mathematical curiosity. It is not a technology. It is almost certainly not achievable by any civilization, not because it is engineering difficult, but because it requires materials and conditions that probably do not exist. Other proposed faster-than-light schemes face similar problems. Wormholes would require exotic matter to hold them open. Tachyons, hypothetical particles that travel faster than light, have never been observed and probably cannot exist stably. Quantum entanglement does not transmit information, so it cannot be used for communication, let alone travel. The speed of light barrier is real. It is the barrier that all plausible physics respects. Any future civilization operating within the laws of physics as we understand them will be limited by it. The second wall is stranger, less intuitive, and in some ways more absolute than the speed of light. The universe is expanding. This is one of those facts that has entered general knowledge without most people actually understanding what it means. The universe is expanding. Galaxies are moving apart. The universe is getting bigger. Most people hear this and imagine something like an explosion with galaxies flying outward through a pre-existing space. That picture is wrong, and the correct picture is much stranger. The universe is not expanding into anything. Space itself is expanding. The distance between galaxies is growing, not because the galaxies are moving through space, but because the space between them is getting larger. This was discovered in the 1920s. The story begins not with Edwin Hubble, who gets most of the credit, but with a Belgian priest and physicist named Georges Lemaitre. In 1927, 2 years before Hubble's famous paper, Lemaitre published a derivation showing that the universe must be expanding based on Einstein's own equations of general relativity. Einstein himself had resisted this conclusion, preferring a static universe and introducing his cosmological constant specifically to prevent it. When Lemaitre presented his work, Einstein famously told him, "Your mathematics is correct, but your physics is abominable." In 1929, Edwin Hubble, working at the Mount Wilson Observatory in California, published the observational confirmation. Using the then largest telescope in the world, Hubble measured the light from dozens of distant galaxies and found that the spectra were shifted toward the red end of the visible range. This redshift was interpreted as a Doppler effect, suggesting the galaxies were moving away from us. More importantly, Hubble found that the farther a galaxy was, the faster it was moving away. This linear relationship between distance and recession velocity became known as Hubble's law, though the mathematics behind it had been derived by Lemaitre first, and is now sometimes called the Hubble-Lemaitre law by more careful historians. The linearity of this relationship, that more distant galaxies recede faster in direct proportion to their distance, is extraordinarily important. It tells us that the universe is not just expanding away from us in some special way. It is expanding uniformly in every direction for every observer. A civilization in a distant galaxy looking back at us would see our galaxy receding from them at the same rate. The mathematical description of this expansion is not galaxies moving through space. It is space itself growing between galaxies. The distinction matters because it has consequences. In a moving through space picture, the speed of a receding galaxy is limited by the speed of light. Nothing can move through space faster than that. In an expanding space picture, there is no such limit. The expansion is not motion through space. It is the creation of new space between objects. And there is no fundamental reason the rate of space creation has to be limited by the speed of light. In fact, it is not limited by the speed of light. At a certain distance from us, the cumulative expansion of space adds up to a recession velocity that exceeds the speed of light. Galaxies beyond that distance are receding from us faster than light can travel. Not because they are moving through space faster than light. They are not. In their own local frame, they are barely moving at all. But the space between us and them is growing fast enough that the effective distance between us is increasing faster than light can cross it. This is not a hypothetical. It is happening now. The universe is large enough and expanding fast enough that at a certain distance, recession velocities exceed the speed of light. The distance at which this happens is called the Hubble radius. It is currently about 14.5 billion light years. Galaxies beyond this distance are right now receding from us faster than light. Now, the Hubble radius is not the limit of what we can see. We can see light from galaxies much farther away, because the light we see now left them billions of years ago when space had not yet had time to carry them beyond our reach. So our telescopes can see galaxies out to about 46 billion light years away, the edge of the observable universe. But the Hubble radius is the limit of what we can reach. It is the limit of what we can send light to or receive new signals from. Galaxies beyond 14.5 billion light years are accelerating away from us faster than light can cross the gap. We can see them as they were billions of years ago, but we can never send anything to them. We can never receive anything new from them. They are for all practical and physical purposes causally disconnected from us, and the Hubble radius is shrinking. This is the key point that most people miss. The universe is not just expanding, the expansion is accelerating, driven by something we call dark energy. The expansion rate is increasing over time. This means that more and more of the universe is being swept beyond our reach as time passes. Every second, galaxies that were once reachable pass over the Hubble horizon and become forever unreachable. This is not a slow process. It is happening constantly. The universe we can possibly interact with is getting smaller every moment. Eventually, in the distant future, the only galaxies we will be able to reach are the ones gravitationally bound to us in what is called the local group. That includes the Milky Way, Andromeda, the Triangulum galaxy, and about 80 smaller galaxies in our gravitational neighborhood. Everything else will have been carried beyond the Hubble horizon by the accelerating expansion. Even if we could solve the speed of light problem, even if we could build relativistic starships that could carry humans between stars at 99% of the speed of light, we could not use those ships to leave our galaxy because the intergalactic distances are expanding faster than any ship could cross them. The expansion of space is an invisible treadmill carrying our neighbors away from us faster than we could ever chase them. To understand why this is so devastating, we need to understand how the expansion works over very long time scales, and we need a better picture than the ordinary Doppler intuition. The standard analogy for cosmic expansion is the inflating balloon. Imagine a balloon with dots drawn on its surface. As you inflate the balloon, the dots move apart, but the dots are not moving across the surface of the balloon. The surface itself is expanding, and the dots are carried along with it. From the perspective of any dot on the balloon, every other dot is moving away. And the farther apart two dots are, the faster they seem to recede because there is more expanding surface between them. This analogy gets across the basic idea. It has two failures, however, that are worth naming. First, the balloon has a center and an edge, while our universe has neither. The expansion does not emanate from some central point. It is happening everywhere at once. Second, the dots on a balloon are carried by the stretching of the rubber, while galaxies in our universe are not dragged through any material. Space is not a medium. It is the geometry of relations between things, and that geometry is changing. A better analogy for mathematicians is the stretching of a coordinate grid. Imagine drawing a grid on a piece of rubber with dots at the intersections. If you stretch the rubber uniformly, the dots move apart, but nothing is actually moving through the grid. The grid itself is expanding. Every dot is in the same grid line it was in before. The numbers labeling the grid lines have simply gotten farther apart. This is closer to what is happening in our universe. Galaxies keep the same cosmic coordinates they have always had. The coordinates themselves represent larger physical distances over time. Two galaxies that were a certain number of coordinate units apart when the universe was young are still the same number of coordinate units apart now, but those coordinate units have stretched, so the physical distance between them has grown. Cosmologists use terms like comoving distance to describe distances in these stretching coordinates and proper distance to describe the actual physical separation at a given moment. The comoving distance to a galaxy typically stays constant or nearly so. The proper distance grows over time as space expands. Right now the Hubble constant is approximately 70 kilometers per second per megaparsec. That unit is confusing, so here is a translation. It means that for every megaparsec of distance, which is about 3.26 million light-years, galaxies recede from us at 70 kilometers per second. A galaxy 10 megaparsecs away recedes at 700 kilometers per second. A galaxy 100 megaparsecs away recedes at 7,000 kilometers per second. A galaxy about 4,300 megaparsecs away, or about 14 billion light-years, recedes at the speed of light. Galaxies beyond that recede faster, much faster. A galaxy 10 billion light-years away, for example, recedes at roughly 2.3 times the speed of light in the expansion-driven sense. We still see it. We see it as it was billions of years ago from light that left it, when the distance was shorter, before the expansion had carried it so far away. But any signal we send to it today would never reach it. The gap is growing faster than light can cross, and the expansion is accelerating. This is important. For most of the history of cosmology, astronomers assumed that the expansion was slowing down. The universe had started with the Big Bang, which gave it an initial expansion velocity, and gravity should have been pulling all the matter in the universe back toward itself, slowing the expansion over time, depending on how much matter was in the universe. The expansion might eventually stop and reverse, leading to a big crunch, or it might continue forever but slow asymptotically towards zero. In 1998, two independent teams of astronomers discovered that this assumption was wrong. One team was led by Saul Perlmutter at Lawrence Berkeley National Laboratory. The other was led by Brian Schmidt at the Australian National University and Adam Rias at the Space Telescope Science Institute. The two teams had been racing each other for years, using slightly different methods, each unaware of how far the other had progressed. When they finally compared results at a conference in early 1998, both teams had arrived independently at the same stunning conclusion. They were using Type Ia supernovae, a specific kind of exploding star whose brightness is extremely predictable, to measure distances to galaxies billions of light-years away. Type Ia supernovae occur when a white dwarf star in a binary system accumulates mass from its companion until it exceeds a critical threshold called the Chandrasekhar limit, at which point it undergoes runaway thermonuclear detonation. Because the explosion always occurs at roughly the same mass, it always releases roughly the same amount of energy. They are, in the jargon, standard candles, objects whose intrinsic brightness is known so that their apparent brightness tells us their distance. What the two teams found was that these distant supernovae were dimmer than they should have been in a decelerating universe. A supernova at a known redshift, assuming standard deceleration, should have been at a certain distance, and therefore a certain apparent brightness. The supernovae they measured were farther away than that. The only way to explain the observations was, if the expansion was not slowing down, it was speeding up. Something was causing the universe to accelerate its expansion. That something was named dark energy because we did not know what it was, and we still do not fully understand it. What we know is that it is a property of space itself. The more space there is, the more dark energy there is, and dark energy causes repulsion, pushing everything apart. This creates a positive feedback loop. As the universe expands, there is more space. More space means more dark energy. More dark energy means faster expansion. Faster expansion creates more space, and so on. This discovery won the 2011 Nobel Prize in Physics for Perlmutter, Schmidt and Rias. More importantly, for our purposes, it changed what we believe about the future of the universe. In a decelerating universe, gravity would eventually win. The expansion would slow. The universe might reverse and recollapse, or at least it would slow enough that distant galaxies might eventually be approached, even if only on timescales of trillions of years. In an accelerating universe, the opposite happens. The expansion wins. Distant galaxies accelerate away from us faster and faster. The Hubble horizon shrinks. More and more of the universe becomes unreachable. This is the trajectory we are on. The universe will not reach a stable size. It will not slow down. It will expand faster and faster forever, carrying everything not gravitationally bound to us away into the darkness. For local structures, this does not matter. Gravity binds galaxies into groups, and those groups are gravitationally bound together. The Milky Way and Andromeda, for instance, will not fly apart. They are on a collision course and will merge in about 4 billion years. The local group as a whole will eventually coalesce into a single giant galaxy. All that is safe from the expansion, because gravity is stronger than dark energy at short distances. But on intergalactic scales between galaxy groups, dark energy wins. The groups fly apart. The space between them grows. And as we saw, that growth accelerates. So even if our descendants build relativistic starships and set out to explore the universe, they will find that most of the universe is already fleeing from them faster than they can chase. The vast majority of the hundreds of billions of galaxies they can see through telescopes are already beyond any possible reach. How much is already gone? This brings us to the third wall, the cosmic event horizon, the observable universe, the volume of space from which light has had time to reach us since the Big Bang, contains hundreds of billions of galaxies. Some recent estimates put the number at closer to 2 trillion. Each of those galaxies contains on average about 100 billion stars. Many of those stars have planets. Some of those planets may have life. All of it is visible to us, at least in principle. Our telescopes can see light from galaxies that were at distances as far as 46 billion light-years away at the time the light was emitted. Some of those galaxies, of course, have moved much further away in the time since the light left them, but the light carries information about them and we can study it. Seeing is not the same as reaching, however. Of those hundreds of billions of galaxies visible to us, most of them are already beyond our possible reach. They are beyond the cosmic event horizon. The cosmic event horizon is a slightly different concept from the Hubble radius, and it is worth distinguishing between them carefully. The Hubble radius is the current distance at which recession velocity equals the speed of light. It is about 14.5 billion light-years. Galaxies beyond the current Hubble radius are receding faster than light right now. The cosmic event horizon is the distance at which light emitted today from a distant galaxy could theoretically still reach us at some point in the infinite future. It takes into account how the Hubble radius changes over time. Because the expansion is accelerating, the Hubble radius is actually shrinking in moving coordinates, the coordinates that track objects as they are carried by the expansion. This means that some galaxies within the current Hubble radius will eventually cross beyond it as the expansion accelerates. The cosmic event horizon, calculated with our best current understanding of dark energy, is at about 16.5 billion light-years. Galaxies beyond this distance, even if we sent a signal at the speed of light today, would never receive it because the space between us and them would expand faster than the signal could cross. The sphere of galaxies within the cosmic event horizon is what we can potentially ever reach or interact with. Everything beyond it is permanently causally disconnected from us. How much of the universe is beyond this horizon? The answer is staggering. Of the 2 trillion galaxies in the observable universe, approximately 94% are already beyond the cosmic event horizon. They are unreachable, not difficult to reach, unreachable in principle. Even if we launched a signal today at the speed of light, it would never arrive. Even if we built a spaceship that could travel at the speed of light, it would never get there. Put this a different way. Of every 100 galaxies you see in a photograph of the deep sky, 94 of them are permanently unreachable. They are on our side of the observable universe because their light has had time to reach us since the Big Bang. But the space between us and them has been growing and is growing faster than any signal can travel. They are gone. They will always be gone. No technology, no matter how advanced, will ever change this. Of the remaining 6%, most are far away and difficult to reach. The only realistically accessible galaxies are the ones in our local group, about 80 or so galaxies gravitationally bound to the Milky Way. Out of 2 trillion galaxies in the observable universe, 80 are actually reachable. That is less than 1/10,000,000,000th of 1% of the galaxies we can see. This is the scale of the trap we are in. When you look at a photo from the Hubble Space Telescope or the James Webb Space Telescope showing thousands of galaxies spread across the field of view, what you are actually looking at is an illusion of accessibility. All those galaxies are visible. Their light has reached us. They are, in the sense of being seen, present in our universe. But they are not reachable. They are light emitted by objects that have since been carried far beyond anywhere we could ever physically visit. The photo shows us the past. It shows us what those galaxies looked like billions of years ago. The galaxies themselves in their current forms are almost all beyond our reach forever. To grasp how quickly things disappear across this horizon, consider a specific example. The galaxy GNZ11, one of the most distant objects ever identified, emitted the light we now receive about 13.4 billion years ago, when the universe was only 400 million years old. At the time, that galaxy was only about 2.5 billion light-years from what would become our location. Today, after 13 billion years of cosmic expansion, it is roughly 32 billion light-years away in proper distance, far beyond the cosmic event horizon. Any signal we sent to it today would never arrive. In fact, the photons we are receiving from it right now are the last photons we will ever receive from any event in that galaxy's history that occurred near the time of emission. Everything that has happened in GNZ11 since then, which is to say nearly all of its history, is happening in causal isolation from us. From our reference frame, it might as well not exist at all. Almost every galaxy in every deep field image falls into this category. The James Webb Deep Field images show us thousands of galaxies across the early universe. Almost every one of them has been gone from our causal reach for billions of years. We are not just locked in our own galaxy, we are locked out of 94% of the universe we can see. The universe is, by any meaningful measure, almost entirely closed to us, And it is getting worse because the expansion is accelerating. The cosmic event horizon is moving inward. What is reachable today will not be reachable tomorrow. Every moment, some galaxies somewhere in the universe are crossing over the cosmic event horizon and becoming permanently out of reach. The rate of this loss is slow by human standards. A galaxy at the current horizon takes billions of years to fully disappear from reachability. But over cosmic time, the effect is enormous. Over tens of billions of years, the cosmic event horizon will shrink until it no longer contains any galaxies outside our own local group. This is the fate of the universe. Not a big crunch where everything comes back together. Not a steady state where things remain as they are. An ever-accelerating expansion where every structure not gravitationally bound to us is carried beyond our reach until the only galaxy we are left with is our own. Well, not quite our own. The Milky Way and Andromeda are on a collision course. They will meet in about 4 billion years and merge over a period of several billion years into a single galaxy, sometimes called Milky Way. The rest of the local group, including the triangulum and the smaller dwarf galaxies, will be gravitationally pulled into the merger over tens of billions of years. The result will be one large elliptical galaxy a few million light years across, isolated in an otherwise empty sky. Around the merged galaxy, if any civilization still exists there, the universe will look very different from what we see now. Currently, the night sky contains billions of galaxies. We cannot see most of them with the naked eye, but they are there. They are part of our cosmic neighborhood. The Andromeda galaxy is visible on a dark night as a small smudge of light. The Milky Way itself is visible as a band across the sky. Through a telescope, the universe reveals itself to be populated with countless other galaxies, some large and bright, most small and faint, stretching out in all directions. In the far future, the night sky of Milky Way will contain only the stars of the merged galaxy itself. Everything else will be gone. The other galaxies will have been carried beyond the cosmic event horizon by the expansion. Their light, which currently reaches us, will be redshifted to frequencies so low as to be effectively invisible. The universe will look like a single galaxy in an otherwise empty black void. This is the fourth wall. Imagine a civilization arising on a planet in Milky Way 100 billion years from now. Its scientists develop telescopes. They look up. They study the night sky. They cannot see any other galaxy because all of them have been carried beyond the cosmic event horizon and are no longer visible. The universe to them consists of a single galaxy surrounded by an empty, dark, apparently infinite void. Their cosmology, developed from observation, will be fundamentally different from ours. They will conclude reasonably that the universe is one galaxy. They will study their local stars, measure distances within their galaxy, develop theories of stellar evolution and physics. Those theories will be largely accurate, but their picture of the universe as a whole will be profoundly, irrecoverably wrong. They will not know that their galaxy was once part of a vast cosmic web containing trillions of galaxies. They will not know about dark energy because they will not be able to see the effects of it in their universe. On the scale they can observe, dark energy does nothing visible. Without other galaxies to measure, they have no way to detect the expansion. The universe will appear static to them because everything not in their galaxy has already been swept out of sight. They will even lose access to the oldest evidence we currently possess. The cosmic microwave background, the radiation left over from the Big Bang, will continue to redshift over time. Today, we detect it as microwaves at a temperature of about 2.7 Kelvin. A trillion years from now, It will be stretched to wavelengths of kilometers with a temperature so close to absolute zero that no detector built of ordinary matter could measure it. The primordial light that tells us our universe had a beginning will fade below the thermal noise of any possible instrument. That evidence simply will not be there to be found. This is not just a loss of information, it is a loss of the ability to know what kind of universe one lives in. Future civilizations will have no way to reconstruct the history we have access to today. They will be unable to measure the Hubble constant because there will be no galaxies outside their own from which to measure it. They will be unable to test general relativity on cosmological scales because there will be no cosmological scale available to test. Whole branches of physics that we take for granted will be for them unreachable. This is the long-term fate of the universe. The accelerating expansion carries all distant structures beyond the cosmic event horizon. The universe in any locality becomes more isolated over time. Future civilizations will see a smaller and smaller sliver of the universe as their observational window closes. In the very far future, tens of trillions of years from now, even the stars in Milky Way will have exhausted their fuel. The age of stars will end. The universe will enter a phase called the degenerate era, populated by stellar remnants, white dwarfs, neutron stars, black holes. No new stars will form because all the gas will have been locked up in dead stellar remnants. Even those remnants will eventually decay over timescales so long they are hard to write down without scientific notation. Black holes will evaporate through Hawking radiation. Stephen Hawking's 1974 discovery that black holes are not completely black, that they radiate weakly because of quantum effects at their event horizons, means that no matter how isolated and stable a black hole appears, it is slowly losing mass. The largest supermassive black holes, millions or billions of times the mass of the Sun, will take roughly 10 to the power of 100 years to fully evaporate. That is 1 followed by 100 zeros. After that, nothing. The universe will be populated by a diffuse sea of photons, neutrinos, and occasional leftover particles drifting in an ever-expanding void. This is called the heat death of the universe. Though the name is misleading, it is not hot, it is absolutely cold. The universe will approach a state of maximum entropy and minimum temperature where no further complexity can ever emerge. This is the ultimate fate, not just of the Milky Way, but of all matter and energy in the universe. Eventual complete irreversible isolation and decay. But for us, the heat death is trillions of years away. The immediate concern is the accelerating expansion carrying the rest of the universe out of our reach. The walls of the universe do not just constrain where we can go. They define the very nature of our existence in the cosmos. We live in a universe that is vast beyond measure, a universe containing trillions of galaxies, each containing billions of stars, each potentially hosting planets with their own complex chemistry and possibly life. A universe with a scale that exceeds anything the human imagination can fully hold, and almost all of that universe is closed to us. 94% of the galaxies we can see are already beyond our reach. The rest, apart from our own local group, are difficult to reach even in principle. The expansion of space is carrying everything away from us. The cosmic event horizon is shrinking. Our effective universe is contracting. We are confined not to Earth, not to the solar system, but to our galaxy and its immediate neighbors. That is our maximum possible domain. No amount of engineering will change this. No future physics will open new doors. The walls are fundamental. Within that domain, we have enormous possibility. The Milky Way and its neighbors contain 1 trillion stars. Most of those stars have planets. Many of those planets are potentially habitable. A civilization with access to all this has more than enough to work with. The galaxy could occupy us for billions of years, but we should not think of ourselves as the future of the universe. We are at most the future of a small corner of it. The rest of the cosmos, the 94% and growing, has its own evolution. Perhaps other civilizations exist in those distant regions. Perhaps they look out at their own confinement and wonder about us, though they too cannot reach us. The universe has been divided by physics into causally isolated pockets, each containing whatever is within, never to interact with the others. In our pocket, we have the Milky Way. We have Andromeda, which will merge with us. We have a few dozen smaller galaxies. We have billions of stars and potentially billions of planets. We have billions of years to explore, to colonize, to develop. Beyond our pocket, there is light. Ancient light from galaxies that have moved on, telling us about a universe that once was but can no longer be visited. This light is a gift. It tells us that we are not alone in the structural sense, that the universe is full of other places like ours. Even if we cannot reach them, it reveals a cosmic history we could not otherwise know. It shows us through telescopes a reality so much larger than our daily lives that it gives perspective on everything we do. We are small, we are confined, and we are lucky. Lucky to exist in an era when the universe is still visible. Lucky to have the tools to read its light. Lucky to have the mathematics to understand what we are seeing. Future civilizations, if any come after us, will not have our luck. They will see a smaller universe, they will know less. The cosmic event horizon will have contracted. The stars will have dimmed. The information will have degraded. We are the privileged witnesses of a universe that is closing. We are seeing the show at its peak. In many ways, this is a better position to be in than being able to travel anywhere. Travel would let us go to one place. Seeing lets us know about everywhere. Perhaps that is the consolation. We cannot leave, but we can see. We cannot visit the distant galaxies, but we can study them, understand them, learn from them. Their light reaches us and tells us a story. The story is bigger than any story humanity has ever told about itself. It is the story of the universe, and we are part of it for this brief window of cosmic time. That is something worth holding, even knowing the walls, even knowing that we will never truly leave the island we live on. The island is the only home we will ever have, and from its shores, we can see oceans we will never cross, and stars we will never visit, and galaxies that have already faded beyond the horizon and the universe as it was when it was young. We are here, we are seeing it. That in itself is remarkable. The walls are real, they are not escapable. But the view from inside is magnificent, and the rooms we have within are vast. The Milky Way, Andromeda coming, the local group ours. Trillions of stars, billions of planets, billions of years. Enough. Enough to do anything any civilization has ever dreamed of. Enough to last longer than any species has any right to hope for. Enough to matter. Even in a universe that is so much bigger than us, we are trapped. We are trapped in a cosmic paradise. And it is ours if we can learn to appreciate it for what it is.